Hey, I wanted to tell you about something we've been working on this semester. It's a story that starts with us trying to automatically remove some supports from a 3D print. And it ends with, well, you'll see. As funny as it is, this all starts out with the crackpot idea we had. Could you 3D print an instrument out of PLA, and then have the 3D printer perform a short piece on it, all without any human intervention? This idea represented a lot of challenges. How could we get a musical tone out of PLA? How would we assemble an instrument with just a printer? And finally, how would we play that musical instrument? Maybe we could have some kind of print-in-place music box that the printer could operate using the tip of its nozzle. Or maybe it would be possible to make some kind of vibrating string using custom print settings. Ultimately, the most viable option we came up with was this, a simple cantilever. We found out pretty early that a cantilever, when stuck to the build plate, created noticeable musical tones when plucked, kind of like a music box placed on a table. It would probably be possible to create a set of musical intervals out of cantilever beams with differing lengths. Kind of like a kalimba, but made out of plastic. So that was our challenge. We would have to find a way to print cantilever beams, remove the support structures holding them up, and then somehow pluck notes on them using the 3D printer. The first step in our journey is the supports. Normal Cura supports are effective at their job, but even when fully optimized for fragility, we found them dense and rigid, making it difficult for a machine to remove them. The first step in our automatic musical instrument is therefore finding a support structure that would more easily break away while still holding up any overhangs. Luckily for us, such supports already existed. Resin printers, also known as SLA printers, incorporate a different support architecture that consists of branching networks of beams. The plan is that SLA supports, if printed on an FDM machine, would be more fragile and easier to break off. After going into Meshmixer and cooking up some custom supports, we found that these SLA-type supports, when printed with lower density settings, achieved the perfect balance of reliability and removability that we needed. Now, these supports were rather thin, and with the wrong settings, we found that it was definitely possible for them to snap off and fail mid-print. However, it was discovered that when we disabled retraction settings in Cura, the resulting stringing would help hold the individual branches in place, allowing for more consistent prints. While this wouldn't work for any random design, it did help us achieve a lower support density in this case, so we decided to take advantage of the trick. What we had at the end of all of this was a custom support structure that required minimal effort to break off and could easily be cleared out by some sort of rigid tool. This would allow the cantilever to be printed, cleared, and played all automatically. But wait, how are we going to do that anyways? This brings us to part 2, the carriage tool. This is an FDM machine's add-on tab for its bed leveling sensor. It also serves as a great starting point for designing a custom tool that could break the supports of the cantilever and play it like a musical instrument. This was a bit harder than you might expect, and we ended up going through a lot of design iterations. Our very first prototype looked like this, and was ostensibly a proof of concept to see if our idea would work at all. We confirmed that the approach was indeed viable, but it left some problems that needed to be addressed. The top of the tool needed to provide a rigid connection so that the printer could remove it from the build plate. To this end, the tool was designed to snap onto the add-on tab. After multiple iterations, this included compliant locking mechanisms and several chamfers to help with locating the tab. Meanwhile, the bottom of the tool was optimized across multiple iterations to have minimal area and maximum fracture characteristics. Finally, this angled corner feature was added because it greatly increased crack propagation during removal. All of these features were added across countless iterations before finally arriving at our final design. This is the tool that we would be using to break away the supports and pluck the cantilever beam. All that was left to do was to bring it together with a little bit of G-code. There were 3 custom G-code scripts that needed to be designed for this project. The docking script for connecting and removing the carriage tool from the build plate, the support clearing script for breaking away custom support structures, and the performance script for playing the instrument. The third script, at this point, was going to be regarded as optional due to time considerations. Let's start with the docking script. You'll notice that there's this tiny point at the very top of the carriage tool. When the printer finishes the carriage tool, the nozzle ends on this point, leaving it aligned with the tool in the y-axis. Then, all you need to do is simply move the nozzle the right amount in the x-axis and you're set. The benefit of this is that we get to use relative positioning, meaning this G-code script works anywhere on the build plate. From there, the printer carriage carefully lowers a set distance to lock with the tool. Then, it fractures the tool off of the build plate, moving very slowly to facilitate crack propagation. With the tool docked, we're now ready to move on to the support clearing script. This step requires the tool to be aligned with the cantilever in absolute coordinates. After that, it performs a support clearing path in relative coordinates. As you can see here, this consists of a braking step where the tool runs into the supports to fracture them, followed by a clearing step where the printer sweeps away the broken debris laterally. These two steps are repeated until all of the support is cleared. Ultimately, we didn't get around to scripting the performance G-code for playing the cantilever. When designed though, this would likely consist of a positioning step where the tool is placed just above the cantilever in absolute coordinates, followed by a plucking step where the tool is moved down and backwards simultaneously in relative coordinates to deform and subsequently release the cantilever. If the coordinate of each cantilever tip was known, a simple Excel program could be written to convert simple sheet music into G-code. So that was how our G-code came together. It wasn't perfect, and it required a lot of trial and error, but all things considered, the G-code successfully carried out the required tasks quite well. We hope that in the future, a more sophisticated program could be designed to algorithmically generate similar post-processing steps for a wide variety of parts. This brings us to the end of our research project. We learned so much this semester, and there's a lot more to do in the future as well. Our custom tool changes for automated post-processing, assembly, and operation are far from perfect. The tool, for one, has to be printed in a specific orientation, and it can't even reach the rightmost side of the build plate. In addition, it has a limited degree of freedom, and is pretty slow moving in the z-axis as well. However, despite all of this, I think they provide a pretty cool vision for the future of 3D printing, where your machine can custom print its own tools, opening up a world of possibilities. I hope that in the future, we can see 3D printers come outfitted with technology that better facilitates these tool changes, so that we can graduate from bootlegging our BL Touch sensors into a world of maker-empowered open-source manufacturing. I genuinely think that technology like this, when combined with recycled material FDM printing, could be pretty useful in environments with limited equipment and human access, like the International Space Station. Anyways, I'm getting ahead of myself. Thank you for making it to the end of this video, and I hope you learned something. I'm Luca, and I'll see you again soon.